Okay, so if they do cancel tomorrow, then in class can't take the test, right? You all still could, but that wouldn't be fair to you to make you take a test that's going to possibly adversely affect your grade and they get away with it scot-free. So, right, that's not fair. So I'm thinking what I'll do if they cancel tomorrow, which I don't think they will, then I'll probably just punt on the daggone test and we'll make the take-home test, the test, still worth 100 points, same. And then they'll hand in their packet, which they can stop by my class Thursday or Friday, and they hand in their packet if they think it's going to help their grade. If they're out of an A, then because I can't force them to come Thursday, Friday. I mean, that's if they had A or B, they didn't have to come Thursday, Friday. Now I'm going to make them come. It'll be too much of a communication issue. I think they won't cancel school totally. I think tomorrow they'll have a virtual day. I don't know what their schedule would be for that. So you all are sort of riding tail on what they do. Let's assume everything's normal, and then we do our usual. You would stop by the front porch Thursday, starting at 1 p.m. Drop off your packet, drop off your notes, pick up the test, and then take an hour on the test, then turn it in. And then 5 to 5:30 on Friday, we'll do about a 30-minute special virtual black and blue. And I'll explain how that works later. Because you won't have your test. But I got a way to do it. Okay. So that's where we're at now. I guess we'll just, I imagine by 6 p.m. tonight, they usually announce by 6 p.m. So then I'll know if they say, okay, we're on. Then I guess I'm pulling an all-nighter. I've done it before. All right.
I've got a question.
Yes.
So basically, since for virtual students, we have to turn in our packet and notes on Thursday, and that's when we get the test.
Thursday or Friday. Thursday or Friday.
Yeah. On Canvas, it says that those things are due Wednesday.
It does because it does, but I knew that might cause confusion. But I can only pick one date. And I didn't want to pick Friday because then my kids in class would be turning in on Friday. So for them, it's due, it's due Wednesday. For you, it's due Friday.
Mm-hmm. So if it's, since it'll show up late, it's fine.
Yeah.
On the Canvas, I mean.
Okay. See, the thing is, you're not submitting those. So I know if I won't make them late, they won't, because I won't put it. I mean, I'm the one that inputs those grades if it's handed to me. Canvas doesn't have anything to do with it. I mean, they do, and they keep the grade, but I submit the grade, and I wouldn't say it was late. Turn it on Saturday, it's late. You can turn things in up to Sunday, midnight. You can submit them. Now they are going to be late if you submit things, but on Canvas, like old stuff, like you forgot, say 2.1 or something, you can still submit it up to the 20th. But as far as turning stuff in, you can turn stuff in as well. I wouldn't count anything late that you're turning in now, but if you turn packet 1 in to the porch, there's a few out there who never turn in a packet 1. Say they get religion, they come to Jesus and they come turn in the packet 1. I'll count it late. I mean, I'll accept it. They'll take, I'll give them whatever 60% or something for it. Yeah. So yeah, that's a good point, but don't worry about that. It won't be counted late. I'd rather put on there the first due date than put the last due date. You know what I'm saying? Okay. Yeah. Anything else?
I have a question.
Yeah.
I was wondering if you could send a PDF because I don't want to take 2 trips to your house on Thursday. So could you send a PDF?
Well, suppose you take 1 trip and you just pick up your test and then you PDF me your results. That way, just 1 trip, because you got to turn your packet in anyway. So I'd rather you pick up the test and then finish it, do your hour, take a picture of it, send it to me. I'll print it off, grade it, and then you'll just see your grade. I mean, on the Canvas.
Okay.
That would be 1 trip. I mean, I'd rather if you live far away or you don't want to get out, then at least turn in your packet, turn in your notes, pick up your test, and then that's just one trip. If you can, I appreciate if you bring it back, but if you're not, if it doesn't work, then, or you're going out of town or whatever, then just PDF me, a picture of your test.
Okay. All right.
Okay. All right. There we go. That's all on record. Yep, it's recorded. So now the moment of truth here. Let's see if the screen shares with the cable. If not, we can do the other thing, but oh yeah, how about that? I don't know what was going on yesterday. All right, so this won't take too long. We were a little ahead from the in-class students, so we got to do some wrap-up stuff in here. This shouldn't take as long as normal. Should be done in, I hate to say it, but let's say 40 minutes, 35 to 40 minutes. So Tuesday the 15th. Oh, it's my brother's birthday today. Jeez. Okay. Got a call in. Big news here. I think I may have said something to you guys yesterday. A student from each class came in at lunch yesterday, and they did the ball drop, and they used the third blue equation to I mean, we all talked about it, but I said, hey, I suggest use the third blue. So they found the G in the room to be 9.71. And then some kids today tried to recreate that and weren't having much luck. But I think and I'll give them some points for trying. There was 4 kids in there today trying to do it, and they gave it a really solid effort. But anyway, they weren't getting the results, as good of results, but this group got it. So they got within 1%, which means that all 3 of them get 25 points each bonus. But what this affects you as well. Every student, and I made this announcement last week. I didn't think anybody could do it. Every student now in all my classes gets, even kids I've only seen twice all semester, everybody gets 10 points bonus. So that's why you have this weird on Canvas, this weird 10 points popped up there. Also, I've had some parents email me and say, hey, my son has a C in your class, but he tells me he has a B. Who's right? It's Canvas that is right. Sometimes the Infinite Campus IC is not doing, there's some problems in the syncing between Canvas and Infinite Campus. So it's the Canvas grade. I realize that Infinite Campus is the quote official grade, but really I will make sure that when I'm inputting grades in January, it'll be January. I think our grades are due like January 6th or something. But when I'm putting your grades in, then I will put in the Canvas grades, okay, not the Infinite. If there's any discrepancy, it's the Canvas grade that'll go into your grades. Okay. I was fretting and ranting and raving at lunch today in front of my wife, the poor thing, about this snow and why tomorrow, why. And she said, honey, if it is a snow day, A, you don't have to write test 2B, B, you don't have to grade it. So quit your complaining. Oh, I guess that's true. I hadn't thought about that. So, I mean, I'm not as upset as I was. I was like very upset today in class, thinking, because kids are what are we going to do? What are we going to do? I said, don't worry about it. It's not going to happen. But now it's still snowing, so I don't know. We did this in here yesterday. We did 214, and we did the head to tail. And the classes were in various stages. So we had to go back and do a lot of makeup stuff. So that's why we're not going to have to do as much in here now, because we were the lead class. And then we came down and we did head to tail on that one. And then I talked about it and said, well, there's another way to do this, and that's called component method. And that is the component method. Now, component method, this is probably used, we will use this 70% of the time next semester to add up vectors. Oh, dude, wizzy. Okay, right, that's what we didn't do. All right, one class I forgot to do something there. Anyway, let's look at an example. So this is the IJ thing, right? Any questions? Open the chat here. Any questions on this, on that I roof, J roof, how to add two vectors using, I call it the component method. I also call it the stack and rack method, because you stack them up. And by the way, these are called tensors. Vectors are a simple example. Vectors are a simple example of tensors. And tensors, if you go far in math or farther in a little bit engineering, but like you get a master's, you get a PhD in physics or in some type of engineering, you're going to end up really learning about tensors. And in fact, most video games, all video games that have a physics engine are built off tensors. So look it up. Look up tensors. Maybe if you're looking for something to write about tensors. If you're looking for a page of notes. Oh, by the way, look off of Facebook. I posted Aspen's. That's what I was going. I posted her notes. She sits up front now. Kids move all around the room, and this week she's sitting up front. And I kept looking over her notes, like, oh my gosh, those are amazing. And so I asked her today if I could take pictures of them. There's like eight or nine pages of just amazing. It tells a story. It's some of the best notes I've seen. Also, Miranda's notes. Miranda has her own style and it's very good. So her notes are in there as well. So there's notes in Unit 4 of the Facebook group. If you're desperately looking for about 5 good pages of notes to write. Now, Aspen's notes are so, and Miranda, and anybody else who wants, you could even send me PDFs of your notes if you're really happy with them. And I'll display them and you get points for that. Most people that take amazing notes, though, don't need the points. They got the A's wrapped up. That wasn't an issue. But anyway, hers are really dense. It's just colorful, and she went all this extra research on her own. She's like, what are you writing a textbook here? This is amazing. The stuff she did on G-forces is outrageous. But that's really dense. I don't need 5 pages that dense. Something, but your basic page of notes would be 5 of those usually is enough for 100 points. Now I'm going to show you a practical example of when you would use vectors. Okay, so this would be in your notes. Okay, this is good notes. So write this down. It's a drawing really, which isn't nothing ready to write. So let's look at a car going up an incline, accelerating up an incline. Okay, this is a car accelerating up an incline. Here's my incline. It's some angle theta. Okay, and this is a preview of next semester. We'll do a lot of these. This is called a free body diagram, an put it over here, FBD. Sometimes called a force body diagram. And when you think of physics, mechanics, really you think of free body diagrams. We've done all this kinematics and we set all this stuff up this semester, which thank goodness this semester's over. Now, next semester is going to be, my second semester of physics is so much better than first semester. So if we have a car going up, so whenever there's motion involved, you put a big fat arrow. For now, anyway, we'll change this later. But a big fat, I make them yellow, a big fat yellow arrow. And that is telling me my direction of motion. If there is motion, you'll take a course in college called statics. And statics is all the physics where there's no motion, like of a bridge, or of a building, or of a table where things aren't moving, or a stack of boxes. And I love that course. That's where you learned all about equilibrium, and not dynamic equilibrium, static equilibrium. In chemistry, there's dynamic equilibrium, and in physics there is as well. But I'm talking about static equilibrium where nothing's moving macroscopically. Okay. But this situation is not statics. This is called dynamics. And dynamics means now not only do we have motion, we probably have acceleration. So this is a situation where a car is accelerating up the hill, and the yellow arrow, sometimes I label it DOM, stands for direction of motion. Direction of motion. So the car's accelerating. So in this situation, just so we have this, car accelerating up a hill. Okay, now let's say it's moving really fast. Let's put a speed on it there. Let's go from 70 miles per hour up to, it's in the process. It's a snapshot, and it's going from 70 miles an hour up to 80 miles an hour. So it's in the process of speeding up, okay? So that's what free body diagrams are. They're snapshots. So I take a snapshot of this car. Now, it's gonna have 6 forces on it. 6. And those are represented by vectors, okay? Because a force is a vector. It has both a size, how big the force is, and a direction it's moving or it's acting. So in class, I kind of made them come up with it. You guys can, in the chat, I'll do the first one. First one, the old bingo, the first one's always free. So I'll do the freebie here and the easiest one. And that is, obviously, if it's a car on Earth, it's affected by gravity. So and that's, come on, man. And gravity is always pointed towards the center of the Earth by definition. It is what down is. Now I'll try and I'm not going to be it perfectly to scale. Oh, hold on a minute. Let me give you some more room. Hold on a minute. Let me do something. Hold on a minute. Okay. That's dangerous. Hold on. All right. I got it. I'm just going to wipe this part out. Let me just wipe that out. There we go. I need some room. So on your page, I would be honest with you, I would take up a whole page, at least half a page. Okay. Don't give me a little tiny free body diagram. Be bold. Okay. So I'll put the first one on there, the freebie. I guess I'll use the ruler that comes with this thing. All right. So I'll put the freebie on there, and that is, by definition, it's a force due to gravity. So whoa, that's a big arrow. Well, I mean, it's a heavy car. So F sub G. Now we're going to call that something else later. But for now, capital F stands for force, sub gravity, force from gravity. Okay, so there's one. And the length of the arrows are important as well. So that's going to be, your car's weight is going to be the biggest arrow. It's going to be the biggest force. You know, we're talking, let's say 2,000 pounds of force. Okay, because if you let it go, if you just put it up and dropped it off a crane, boom, all that force is pulling that car to the earth. So that's there. Now, in the chat, okay, so now Ayo's gotten some traction here, and he's done some reading, I see, because he says that there's also what's called a normal force. Now, we have to counteract that force due to gravity. So this is called the normal force. And that is lowercase n. Now, normal force is called a contact force, okay? It's anytime, like I'm sitting in the chair right now, you're sitting in a chair, there's a contact force pushing, keeping you from falling to the floor, and that's the upward force. Normal force is not always upward, but it's the force that is keeping you from falling to the center of the earth. There's something else I forgot to do. If we're going to make this, we're going to make our life easier, and we are going to tilt the axis. So here is the x-axis. I'll make them purple. And here is the y-axis. So I'm tilting my coordinates. And physicists don't do that to make our life hard. We do it to make our life easier. And this does make your life easier because it reduces the number of angles you got to deal with. So here is the y-axis. Okay, so that's two tensors, two vectors so far. Io also said, well, let's bring in friction. And Jacob said, let's bring in air drag. Okay, I agree with those. So let's go with air drag. Air drag, if I'm going 70 miles an hour, air drag is more important than road friction. So air drag is a force. Now you're going to wonder why I do this. You think all forces should emanate from the same point if I'm going to use the component method, okay? So, okay, so let's make this, that's probably too much, but let's make this my force. Now air drag, we've looked at air drag before. We looked at it on a gold standard. One thing about gold standards, you can preview some stuff. So this air drag, that is R sub A, capital A, lowercase a, either way. So we have air drag back. That's opposing motion. Air drag always opposes the big fat yellow arrow. It always opposes direction motion. And also road friction. So road friction is back. And that at 70 miles an hour, or 75, whatever it is between these two, road friction is not near as important as air drag. Road friction is a little curly f. It's a lowercase curly f. All frictions are lowercase curly f's. Okay. Don't ask me why. That's how I was taught. So your professor may have a different opinion on that, but that's the cool way to do it. So there's 4. We got 2 more to go. Well, let's see what else you guys have said. You said friction is always perpendicular. The normal force, the reason why it's called normal, as Io is alluding to here, the reason why it's called normal is an old mathematical term that means perpendicular. So, well, it's a normal. So it's just a name that's stuck, even though we don't use it otherwise. It's a contact force, normal force to contact force. This will not be on the test tomorrow. I'm giving you a preview of second semester. Well, there's 4 forces. I need 2 more. Let's see what you guys are saying. Okay, I think I know what Eric is saying. Eric is saying there's some kind of force that's causing it to accelerate. If it's going uphill, there has to be a force. Okay, so I'm going to agree with you. There is a force of propulsion up the hill, and that's got to beat both drag and road friction. It's got to beat it because the overall summation of forces is uphill. So we call this force of propulsion, F sub P. Now, here's a rule. Here's a rule. All forces on a free body diagram. Okay, this is worth writing down. All forces on a free body diagram have to be have to be external, meaning they did not come from the object itself. I cannot grab my hair and pull myself to the ceiling. Okay, all internal forces cancel. That's what Isaac Newton taught us back in the late 1600s. So they cannot be internal forces. So saying all that, here's my question. What is the source of that force? What is the source? I can look at this and say, okay, force of gravity, the source is the earth. The normal force, the source is the pavement. Air drag, the source is the air molecules. Road frictions, the source is the road. What's the source of propulsion? You can type it or say it. Your best guess. Source of propulsion. We had this discussion in first.
The engine?
The what?
The engine from the car?
But the engine is the car. Can't be the engine. It's part. The car, okay, the car in this case is a dot. It's a dot. Jacob said, well, the force that reacts with the explosions in the internal combustion engine of the car. But that's still Newton's third law saying that all those internal forces in the engine cancel each other. Or the car would explode. They all cancel each other. So how then does the car get anywhere? And this is apropos for maybe tomorrow morning, trying to go to school or trying to go to the store. If you're, okay, let's say your driveway is just, say it's flat, but it's just ice. And you go out and you turn your car on, you rev your engine, you push on the gas, and all that happens is your tires just spin. See, you can hit that engine all you want and the car ain't gonna move. What does the car have to move? What's the car got to do?
The wheel and axle part?
So, but the wheel and axle is part of the car. It's all one big dot. In other words, what I'm asking is, if I'm driving on I-35, what propels me? What makes me go forward? What makes me go down I-35? It's not my engine. It's not my tires.
Gas?
The what?
Gas?
It's not the gas. I mean, I understand. That's what's little explosions, okay? In the pistons, I get all that. But that's still internal. You know what pushes me down I-35? I-35 itself. The only way I propel myself down I-35 or I accelerate on I-35 is for I-35 to push on me. You have to, it's Newton's third law, but you have to have, for Newton's third law, you have to have two bodies, not one. You have to have two bodies. It's not the earth rotating. It's simply that if I'm going to drive my car down the road, those tires have to push against the road. And the road then reacts to that and pushes back on the car. So you move down a highway because the highway pushes you down the road. So the source here is the road. Okay. Now that's 5 forces, and we'll get into this more next semester. That's 5 forces. There's one more force. Anybody think of the other? And this force doesn't come into play till around 50 miles an hour, depending on the aerodynamics of your car. That's my hint. What's my 6th force here? One more and then we'll move on. I wasn't planning on having this long of a conversation. I guess we're going to go further than I thought. Sorry. What's that 5th force? Not tension, good guess. The tensile forces, if I was being pulled by a rope, if I was being towed, yeah. But tensile forces are a whole special kind of force. It is, in this case, if I'm going that fast, there's a little bit of lift. Now make it small. There's a force of lift. F, it's capital F, then subscript capital L, force of lift. And that's because of something called Bernoulli's, also called Venturi. It's effects of moving air over the top of the car. Daniel Bernoulli figured this out way before we had cars or airplanes. But it's how the airfoil works. It's how an airplane lifts. But a car, especially modern day cars with their with their swept aerodynamics. The problem with that is the car tends to act like an airplane wing at high speeds. And so how do they counter that? There's two ways they counter that. This is the last thing we'll talk about, and then I'll move on. Two ways to counter your car being lifted off the ground as you drive fast. Think of a F1 racer, or think of a NASCAR. How do they counter? They're going close to 200 miles an hour. Well, you don't want to do that. You can make it less aerodynamics, but then you're going to pay the huge price. Well, in a way, you are doing that, but you can't. You want to break into the wind fast. You don't want like a semi truck. Even semi trucks now are built to be aerodynamic, but it's not that, because it really just destroys your gas mileage. But you got to keep those back tires in the ground. Two things to combat force of lift. What is going on? That ruler is not working lately. I'm going to have to write a letter. Force of lift. Two things. Yeah, you want to have a downward force. So two things to combat force of lift. Combat it with spoilers, a spoiler, and an air dam. A spoiler on the back of the car, an air dam on the front, and the lower, the grill. You see NASCAR, and I do pictures of all this. We go through all this next semester. But those two things keep the car settled on the ground and keep it from lifting up. And I have video of cars just going so fast, they just start flying. And once you fly up and you get a little bit of angle, all that air grabs the bottom of your car and just flips it. You see it in cigarette boats too, Okay, that was a preview of second semester. Preview of spring physics. Okay. Well, let's go back to the fall here for a second, and let's do one more problem. Our last official problem of the first semester. And so we're on 216. We're only going to get one problem done on 216. I'll probably throw 216 at you again in January, just because we didn't get enough done. So we're going to go from the orange to the blue, like we've already done. We did this yesterday. V naught, just put it up here just to have it. V naught y minus GT. This is delta y equals V naught y t minus 1/2 GT squared. And then we have V final. Sorry, it's buffering. And then we have V. Let you catch up. We have V final y squared equals V naught y squared minus 2g delta y. Okay, we're going to work number 2. We'll skip 1 for now, and let's work number 2. Now you're going to need a little extra room on the right side of number 2. So you could just do it in your, you're running a room there. You just want to do this in your notes as well and beef those notes up some more. Okay, so number 2, we have a ball that's thrown vertically downward from the top of the building at 14 meters a second and hits the ground in 5 seconds. So on this, that's the problem with putting all four classes on one page. On this one, let's make each one of these little dots here, let's make this it'll represent different things. But as far as velocity goes, let's make each one of these little ticks represent 10 meters a second. So first thing we're going to do it eventually anyway. Let's give the vector. So the first vector is, and yours is tiny, I know, but the first vector is 14 for velocity. The first vector is 14 negative V naught y is negative 14 meters per second. So you threw the ball down. This will be our V column. We'll have a delta Y. Oh boy. Daggone it. If it's not too late, let me. If it's too late, you didn't pin. Don't worry about it. I think I want to make this column the delta Y, the Y column, the delta Y column, and I'll make this a column move over a few, and I'll make this my velocity area down here, and then over here I'm going to make this the next. There'll be 3 columns, and the next one I'm going to make. I'll do it in orange, I guess, red, and I'll make this my acceleration column. Okay. So the first velocity is 14, negative 14. So it's going to, if each one of those is 10 meters a second, it's going to be at about that length. So that is V naught. Trying to make this look nice since this is a V naught Y. This is the official record of what happened in class. V naught Y equals 14, negative 14 meters per second. Okay. Just setting it up here. The time, it looks like it took it 5 seconds to hit the ground. That's a pretty tall building. So T equals 5 seconds. Because remember, when we dropped a ball, well, you weren't there, but when we dropped the basketballs off the Harv, that was from the top of the stands. That was about 1.27, 1.3 seconds. So this thing is falling for 5 seconds. Also, very important, assume air drag is minimal. Air drag is, what do we say? It's minimal, but we say you don't worry about it. Man, my brain's fried. It's negligible. Thank you. Negligible. Negligible. Anyway, so don't worry about that. So this is kind of like the Brian Cox video we watched yesterday where they fall in a vacuum. I know it's not a vacuum. And if a building really was tall enough for it take 5 seconds for an object to hit the ground, there would be, not only would there be air drag, there'd be terminal velocity, which we'll talk about more next semester. And that is where air drag counters gravity, and it doesn't speed up anymore. Terminal velocity. That's a whole thing. Okay, we'll spend some time on that. Now, so we're in free fall. If we're using blue, it means there is no air drag. By using blue equations, you're acknowledging no air drag. Okay, so determine the total displacement. So you all now, Jacob said terminal velocity is maximum velocity for a given set of conditions. That's terminal velocity, and terminal velocity means in free fall, not like my terminal velocity of my car driving down the road. It's things that are falling back to Earth or the moon or whatever. Every planet has its own terminal velocity. But anyway, so it has to do with gravity and has to do with air drag and atmosphere and how much atmosphere there is. Forget that. Okay, so it said determine the total displacement. Well, we're going to use, and I sent them to the board. They had to go to the board on A, B, and C. So I'm going to pause it here so we're not boring the people at home, and I'll give you a few minutes to try and do A, B, and C on your own. All right, I'm recording. So we plug in our numbers here and make sure on the V naught, I don't know if you did this, but make sure you make that negative. Negative 14 meters per second times 5 seconds minus 1/2 times 9.81. Don't use negative. G is positive 9.81. It's a magnitude. It's a magnitude. It's a magnitude. G cannot be negative. It's going to burn you big time, man, if you make G negative. You get away with it for a while, and oh my goodness, when we get to pulley systems, ooh, That's going to be ugly. Times for you, if you're making G negative, if you make that assumption. 5 seconds, I know because I speak from experience, squared. Now I'm going to be lazy here, and I'm going to sneak over to the back. Where's the back? Oh. Next page, maybe. I'm going to sneak over to the back, and I'm going to look. Ha! Negative 193. So delta y, then, that's pretty dangerous. That's a bold move because I might have been wrong, but delta y, but I'm not. I've done this enough times. Negative 19. I wouldn't suggest you do that. Negative 193. Do as I say. Not as I do. Negative 193 meters. So there we go. That's that one. I'll highlight that, make it look pretty. And then it says, draw the displacement vector. Okay, so I made them draw a building and draw a displacement vector. And so the displacement vector for my delta y is simply a line that goes all the way from the top where the ball was thrown to the ground. Just draw that down there. Oops. Okay. There's my delta y. Okay. And then it said, how tall is the building? And that's a dumb question. The building's 193 meters tall, but that is H. That's H. And H, lowercase h, stands for height. So that is H. And H is equal to the absolute value of delta y. Delta y you had to show as negative because the origin is the hand. The origin is always the hand, right? So the hand is the origin. So you drop the ball, and then that. But if someone asks, how tall is that building? You don't say, well, it's negative 193 meters. So it's like saying speed is the absolute value of velocity, distance is the absolute value of displacement, height is the absolute value of delta y. So that's positive 193 meters. I mean, that's a tall building. I mean, it's about 3.5 meters a story for a story, first story, second story. So 193 meters is pretty daggone tall. I'm talking like Devon Tower or something. Okay, what is the velocity of the ball halfway down? Now, suggestions? How do I find the velocity of the ball halfway down?
Would you use the first blue equation?
And what? If I did that, what would I
half
do?
of the time.
Cut time in half. Now, let's look at, you couldn't have said it better. I mean, that's wrong, but that was perfect because that's what I was hoping somebody would say. Because that's logical, right? If you're gonna do what you're gonna go half time, right? Makes it easy. Cut time in half, 2.5 seconds, boom. As a lot of students would do on a test. This will not be on the testimonial, if there is a testimonial. So now we need to plot a trio. Now, not this trio up here. This goes to number 1. This is not going to work. A negative trio. So this, in your notes, sketch yourself a negative trio, but you have to be kind of careful as to how. So let me set this up with you. Make it a negative trio on this side over here. Okay. So we'll have our y versus t. We'll have our v. I'll make that y a little bigger. Yeah. V versus t. We'll have our ay versus t. Move that down a little bit. All right. And then now you got to think, what quadrant am I in? I'm going to be in the 4th quadrant for y versus t because the hand is the origin and that's at the beginning. So boom, I'm in the 4th quadrant for the y versus t. I'm in the 4th quadrant for the vy versus t because the ball never went up. And then, of course, so all 3 of these in the 4th quadrant. And this is y meters, whatever, meters, I guess. This is v meters per second, and this is ay meters per second squared. Okay. Kill that. Kill that. Okay. Meters per second squared. Now, of those three, a lot of times on tests, you have to do the problem, then you have to draw the trio. So even when we're doing forces, even next semester, you still, what trio? Yeah, show me the quartet. We got thrust. We got a rocket thrusting. Show me the quartet. What? Yeah, you got to know what's happening dynamically. What's happening? You got to know everything: force, energy, power. What's going on with momentum? But the bottom line is what's going on with observables. What's going on kinematically? And that's what colleges blow through. And then they wonder why students are sitting there struggling, having no idea. Well, you blew through the one thing they could actually see, the one thing they could actually measure. You blew past that and you went to power. And no wonder they're all just going, what's going on? It's my experience. So AY is simply gravity, right? G, the acceleration to gravity. So that one is just flat, but it's negative flat. So right across. Negative G. Okay. Now what about velocity? Vy. This is Vy, not V. There's no Vx here. This is Vy. Where does it start? Oh, so yeah, Jacob said about 55 stories. And that's it. So this would be about the height of the Devon Tower. But where does the velocity start? What's initial velocity?
Negative.
Negative 14, right? So we didn't drop it. So it starts at negative 14 right here, negative 14 meters per second. And then what happens to the velocity as time goes by? It's getting more and more negative, but can you tell me by how much? And my hint is, right. So at 9 meters per second every second, it drops 9 meters, 9.8 meters per second every second, approximately 10. So I know that if it's at negative 14 to begin with, in 5 seconds, 5 times 10 is 50, it's dropped down to about negative 64, somewhere in there. So I already know just from sketching it out that my final velocity will be somewhere around negative 64, something less, 63. So I know that slope, this slope equals negative G, or negative 9.81. So I know this will end up somewhere around negative 64. All I did was a 5 times 10 is 50. So about negative 64, good enough for a graph. Finally, we got to plot the y versus t. Now, what's that look like? It starts at the hand, so it starts at 0. If this is flat, this is linear. If this is negative flat, this is negative linear. What is this?
Negative parabolic.
Negative parabolic. So good. There's a point there for that one. So good. So watch. Don't do this, but watch. I'm going to make a mistake. All right. I did something wrong. Subtly wrong. If this were worth 20 points, you would have just lost 2 points. What was
It should
your
be flipped?
Say it again.
The parabola should be flipped.
Well, it is flipped. I mean, a normal parabola for a trio, the parabola looks like that, right? I did flip it. It's a negative parabola.
Well, I mean, like I guess reverse, where it would start off like the parabola curve would start off down more and
Deep?
then eventually flatten out.
Oh, you're saying it looks like this,
Yeah.
right? Okay, so let's think about this. Which one is it? In this case, the object, if it was like this, the object would start off falling really fast, and as it fell, it would get slower and slower. That's not our experience though, right? So now if I drop a pearl in water, that happens, but that's a whole different ballgame. That's terminal velocity. In this case, it starts off going slow. The slope is small to begin with. It's steeper and steeper, steeper. So good thought, but that is not the case in this case. That's the general shape is okay. It's okay. I think I know what Jacob's saying. He's saying it's parabolic, yes. He said, but it doesn't start at 0 meters a second. It starts with a given slope. So I agree. So actually, it starts with a little bit of a little bit of a slope. So that was, like I say, that was subtle. I'm impressed that anybody could even begin to see that at this point. We'll hit this more in January, but this is not on the test form. So it already starts off with a downward slope and then just gets more and more. So something like that, where it's not flat to begin with. It already has 14. Its initial slope is negative 14, and the slope eventually drops. So the slope right here, this tangent line right here is at negative 64 meters per second. This tangent line up here is at negative 14 meters per second. You see, these ideas that we picked up in October will be applied in January, March, May. They still applied over and over and over again. That's why I'm giving you fundamental things. And then you'll apply it, in electromagnetics. You'll apply it in chemistry. You'll apply it in all kinds of subjects, calculus, All right. That's what I'm trying to do. I'm trying to plant some seeds that grows in about 4 different courses. What's the velocity of the ball halfway down? So that was the question. Well, if I just cut my time in half, if I go half time, notice that is not halfway down. Half time is not even close to halfway down because that is not parabolic. I mean, it is parabolic, and half time, it doesn't work, because if it was linear, that would work, but it's parabolic, and so it's not. This may be t1/2, but this is not halfway down. So the only way to do it is to use the third blue. So we need the third blue for D. Third blue. Hope I'm taping. Yeah, thank goodness. Third blue. So that is V final y squared equals V naught y squared minus 2a delta y. So blah, blah, blah. Okay, we know I plug and chug, I guess. V final y, V final y then is the square root. You got to scroot everything in there. And we have negative 14 meters per second squared minus 2, G, minus 2 times 9.81 meters per second squared times halfway down. So it's really half of delta y. So that's 96.5.
Yeah, you're right.
Say it again.
I say, yeah, you're right.
Yeah, but I'm not. What's my mistake? Boy, this will screw you up.
To be negative.
Thank you. There you go, Rose. Rose pulled that point out. That has to be negative. Okay. Because it fell below. If you make that positive, you're going to get the square root of a negative number, and you go, whoops, that made it right. So you had to make that negative. The signs, man, signs, we're not messing around. Signs will kill you in physics, especially second semester. Sign everywhere, a sign, blocking up the scenery, changing my mind. I don't know what that's, the 5-man electrical band. I forget the name of that, how that song goes. Can't you read the sign? And the sign said you got to have a membership card to get inside. E says, oh, okay, we're almost done. So I put all my hair up under my hat and I went in to ask him why. Okay, so that was a protest song back in the 70s. And I had a lot longer hair back then in the 80s, well, no, late 70s. Okay, so now we go to, we have to draw on our vector chart here. We got to draw the V. So we have V naught at negative 14. We now have, when you plug all that in there, you get cheating here. I look ahead. You get negative. Oh, yeah. You get the square root, but it's negative 45.7, right? You say the square root's a negative number? What's the square root of 4?
Plus or minus 2.
Yeah, right. There's the point. Plus or minus 2, you have the choice. Well, I'm going to take the negative root because I know it's going down. So then halfway down, kind of on our chart here, kind of pick something halfway down. I guess that's close enough. We're going to write our next velocity vector. And that is there. It's now, every one of these is 10. So it's 40, it's 10, 20, 30, 40, 45. So it looks like that. So that's my V half, V at halfway down. Okay. And then E says, I realize it can be misinterpreted here, but I want to know what the velocity is of the ball at the bottom. And students say, well, Mr. Askey, it's 0. The ball hits the ground, it stops. No. That once the ball hits the ground, it's a whole nother set of physics equations, okay? The ball hitting the ground, that's conservation of momentum, that's all kinds of stuff. So we're not dealing with that right now. We're just dealing with the free fall part. So when I say final velocity, I mean the velocity of the ball a microsecond before it hits the ground. So once again, we could do it the same way we did D. We can just use, we can do it either way now. Why not go the simpler route? Why not just go first blue? That's even easier. Let's go first blue. If it's low-hanging fruit, I'm going to go get it. V final Y equals V naught Y minus GT. So simply plug in. So V naught Y is negative 14 meters per second minus 9.81. G is positive. Meters per second squared times 5 seconds. And we get, I think, 63 or something. 63, negative 63.1. So we predicted that, by the way. V final Y is equal to negative 63.1 to 3 siggies meters per second. And over here, we had predicted that already. We said negative 64 because we were estimating G to be about 10. Okay, now we're about done. It says draw the following. We did that. We drew the, then your final velocity right here is going to be 6. We're going to go into the ground. I'm guessing that's about 6. And a student asked me one year, says, you mean the ball's going to put a hole in the ground? Like, no. It's just these vectors are virtual, okay? They're just virtual. They're mathematical representations. The ball is not going to put a big hole in the ground. So that's V final. Kids trying to learn. What am I I'm fine. Oh, final thing we're going to do, and that's on this problem, F. It says now draw the acceleration vector here at these 3 points. Draw the acceleration vector here at the beginning, draw it here at the middle, and draw it here at the end. So let me give you a minute to draw. I'm going to make mine red, to draw the acceleration vector at those 3 points. Oh, Jacob said, where'd I get number 45.7? I got it from the bottom of the back, man. But no, I mean, it should, 45.7 should work. That's the square root of that. Make sure your 96.5 is negative. You should get 45.7. Okay, do you have your acceleration vector? What's the acceleration vector? Someone chime in or chat. What's the acceleration vector at the top? When I first throw the ball down, what's the acceleration vector? We're almost done.
Isn't it just 9.81?
Thank you. Negative G. So let's make it, let's say this is 10. Now I'm using the same graph for different scales, I realize, but so it's negative 9.81 meters per second squared. What is the acceleration vector halfway down? Right here.
Still 9.81.
Negative 9.81. And sure enough, just before it hits the bottom, the acceleration vector is negative 9.81. It don't change. It does, but that building would have to be 500 stories tall to really start to make a noticeable change. Okay. Well, that was a lot. We did, sorry, man. I thought we'd be out here in 30 minutes, but I did the whole thing in the free body diagram. But that was a pretty thorough, that was the best job I've done on this problem all day. So I'm glad about that. We have it recorded. Okay, I'm going to change this for next year, change the sheet. I'll add that trio. All right, thank you all. Any questions in general? Be watching, be listening for the phone call from Norman Public Schools. If they say we're canceled, then all bets are off as far as test 2B goes. The final will still take place for those with a C or D or failing, but that's going to be a final that should help you. I'm going to make it open notes. I'm going to put it on Canvas. I'm going to I'll give you till Friday. You'll have, 24 hours to do it. So it's only worth 100 points. So, but if you're at an 89.1, heck, maybe go for it, right? Can't hurt. 100 points ain't gonna kill you, and it might just give you the A. And it's open notes. So if you take it though, remember, if you take it, I'm counting it. So you can't say take it back. If you're going, it's like a quiz. Okay, it's not something you take a picture of. It'll be like those quizzes we did. So it'll be, so Canvas will grade it. So what do I care? If everybody takes it's fine, but you don't have to. If you have an A or B as of today, then you don't need to take it. Does that make sense? Okay, so that is what's happening. If they don't call school, I guess I'm going to be up all night writing you a really good challenging test 2B, challenging, 200 points. So go ahead and get all your packet together. If they call school, then you're not going to have to turn your packet in. Unless you want to, unless you think it'll help your grade. If you have an A, I wouldn't do it. But you can if you want. It can't hurt. I mean, a packet, I'm not going to let the packet hurt you. Okay. If you have an A, you probably have a good packet. Well, thank you all. You've hung in there. It's been a crazy semester, but you guys have made it. I'd be going stark raving crazy if I was doing this with myself. I couldn't do it. I wouldn't have kept it up. But having you guys, even though I see your names in your picture maybe, but having you guys there has made all the difference. Taki said, okay, so he's talking about the problem. All right. So I think we're getting better at this. You guys, maybe if we do it again next semester, we will do it again. I'll be around. Well, maybe we'll have some new rules on these where chatting becomes more of a thing, and you participate with a greater role. And I'm trying to do better on my part, make it more, more interactive. But a lot of your suggestions will help too. You certainly can make suggestions. You're the one, I don't see it from your end. So I'll ask for your suggestions. Okay, so I'll record this and I'll put this recording on there, and we'll talk the next time, if everything's going cool. The next time we talk in person would be Friday at 5 to 5:30, where we're doing black and blue on test 2B. Okay. So I'll see you. If you don't come there on Friday, then have a good break, and I'll see you in January. Bye-bye.